Welcome to G Fun Facts Online, where we decode the science behind the world we live in. Today, we're diving into a high-stakes, high-speed world that's usually hidden from view, the unseen arms race in military materials. We're talking about the science behind projectiles designed to pierce the toughest armor on the planet. This isn't about bigger explosions. It's about a violent ballet of physics and materials science. This is the story of the kinetic energy penetrator. The basic idea is simple but brutal. Hit a target with so much focused energy that you punch right through it. How do you do that? You take a very dense, very hard projectile, shape it into a long, thin rod, and fire it at hypersonic speeds, several times faster than the speed of sound. All that velocity translates into immense kinetic energy, concentrated onto a single tiny point. For decades, two materials have dominated this field: depleted uranium and tungsten. Let's start with depleted uranium, or DU. This stuff is a byproduct of the uranium enrichment process, and it is incredibly dense. But its real party trick is a property called self-sharpening. As a DU penetrator smashes through armor, the tip fractures in a way that actually keeps it sharp, focusing the force instead of blunting like a normal piece of metal would. To add to the chaos, DU is also pyrophoric, meaning it can burst into flames on impact, causing massive secondary damage inside a tank. Then we have its rival, tungsten heavy alloys. Tungsten is one of the densest elements on the periodic table, and it's exceptionally hard. These alloys, often mixed with nickel or iron, provide a non-radioactive alternative to DU. While they don't have that self-sharpening ability, their sheer hardness allows them to withstand the incredible stress of impact and power through advanced armor. The choice between them involves a complex trade-off. DU has a slight performance edge, but its low-level radioactivity and chemical toxicity pose long-term environmental risks. Because of this, many countries prefer to use the less toxic tungsten alloys. But the story doesn't end there. The quest for an even better penetrator is pushing scientists to explore new materials. Advanced steel alloys, for instance, are still used for smaller rounds and offer a cheaper alternative. And then there's the future: composite materials. Imagine projectiles made from ceramics, carbon fibers, and novel metal alloys, all engineered for specific properties. You could even have a jacketed penetrator with a super dense core surrounded by a lighter, stiffening material. This lets you make the penetrator longer and more stable, which is key to its performance. The design of these things is just as clever as the materials. The most common type is called an APFSDS round. That stands for Armor-Piercing Fin-Stabilized Discarding Sabot. Let's break that down. The penetrator itself is a long, thin dart. To fire it from a wide cannon barrel, it's wrapped in a lightweight casing called a sabot. Once the round leaves the barrel, the sabot pieces fall away, leaving the slender, fin-stabilized dart to fly to the target at incredible speed. When this dart hits the armor, the physics are insane. The pressure and heat are so immense that both the penetrator and the armor can start to behave like fluids. The ability of the projectile to resist deforming and stay on course is what separates a successful penetration from a failure. Of course, this is all part of a constant cat-and-mouse game. As armor gets better, with complex layers of composites and ceramics, the penetrators have to get smarter. The future might even see kinetic energy penetrators with their own guidance systems, allowing them to adjust their path to hit a tank's weakest spot. So the next time you think about military technology, remember that some of the biggest battles are being fought on a microscopic level, in the labs where scientists are forging the next generation of materials. It's a silent arms race, where the unseen edge is made of tungsten, uranium, and the very future of materials science. Thanks for tuning in to G Fun Facts Online. Don't forget to like and subscribe for more deep dives into the science that shapes our world.